Okay, folks, in the last learning goal of this module, we're going to go through how to calculate the photolysis rate constant. So photolysis rate constants are, of course, dependent upon how much light you have, what the molecule is, what the reaction is, etc. So it's not necessarily a given that any one photolysis rate constant will be the same as the other. So typically we see the photolysis rate constant given as Kp, though sometimes it's given as J. So I know there's not enough letters in the alphabet and they often get reused. And so there's two different ways we could calculate the photolysis rate constant. And one using the integral form, which assumes that we have like smooth relationships for infinitesimally small intervals of lambda. The other, which is more common here to use, assumes that we don't have these infinitesimally small relationships with lambda steps, and that we've relied on experimental data. So we're more often than not going to see the summation form used. So if we go through what all of this stuff means, so phi, that is our quantum yield. And you can see it's a function of lambda. And so that would be quantum yield specifically for photochemistry. So very typically, we can assume the quantum yield for photochemistry is 1. Not always, but it's a good assumption. Okay, and we'll get into more of those details why as we go down the rabbit hole. So now sigma as a function of lambda, we talked about that already. That's the absorption cross-section. And right, that is the base E cross-section given in units of square centimeter per molecule. And then finally, that leaves the flux. Okay, and that is how much light we have available. And so now, what I didn't mention here and neglected to, photolysis rate constants are always first order processes with units of 1/seconds. So the quantum yield is going to be unitless. This is going to have units of centimeters squared per molecule. So as we might guess then, flux has to have units of photons per square centimeter per second. Per square centimeter per second. So now the photon unit and the molecule here, that technically cancels through the quantum yield. So in other words, we could really think of the quantum yield as how many molecules were formed over how many photons were absorbed. So the molecule and the molecule will cancel, and the photon and photon will cancel. So we typically have to either know flux or calculate it based on a few assumptions of our lamp. So flux depends on the light source, whether that light source be something in the laboratory or maybe even like the sun if we were thinking about natural photochemistry. And so the way that flux is calculated is the following, and I like to give this as a, I don't have like a fancy formula for it, I just like to say it's power over energy times area. Okay, so power, that's going to depend on the light source. Energy, that's going to depend on the wavelength. And area, that's going to depend on how much area the molecule is illuminated by. All right. So for example, the energy is calculated from hc over lambda. So that's where the wavelength matters. Okay. The area, so and actually probably it's easiest if I draw a picture here. So imagine we've got like some light bulb, right? I'm going to draw just like a very cartoony looking light bulb. And that light bulb is emitting light all around. So what becomes easier to do in a photochemistry experiment is, let's suppose we've got our reaction cell right here. Okay. So if we were to just set this near the lamp, we would certainly get photochemistry going on. However, we would have a hard time calculating exactly how much flux is occurring. So typically what we would do is put this narrow opening right next to it, so that has some type of slit. Okay, and so now only a certain amount of light makes it through. And so the power and the area is given by that. So how much joules per second makes it through that area. And of course, that's given in centimeters squared. And then, of course, that number is technically joules per number, or joules per single photon, right? So for example, let's suppose you've got a 1 watt area being illuminated over 1 square centimeter. So suppose 1 watt over 1 square centimeter. So we could then calculate how much flux there is just with those two numbers and with knowledge of what the wavelength of light is. Okay. So for example, let's move into something with some real numbers that we can play with here. So here we're looking at the sigma base E. So notice there it is, base E cross section of either Cl2 or bromine 2. You can see is also listed there. Let's play with chlorine. So for example, Cl2 plus light to make 2 Cl radicals, right? So how would we calculate Kp from that? Well, if we assume that we had 1 watt over a 1 square centimeter area, that's some pretty good assumptions that we could use. But now we have to get what the cross section is. And if we're doing this experiment, we would want to pick a wavelength where there is a maximum cross section. So in other words, we'd want to pick the lambda max. So now if I scan across this, and you can see this is why we want the sum version, because oftentimes we'll see tables that don't have a smooth continuous set of data, rather it's in these intervals. So now if I'm looking at the Cl2 data, hopefully what you can see here is if I highlight this area at 330 nanometers, that's corresponding to a lambda max for Cl2, right? So presumably, if we could pick that 330 wavelength, that would be ideal for carrying out this reaction. So then, of course, we would calculate how much energy we have using 330 nanometers. Beautiful. And then we would plug in that cross section. And what I want to point out here, this says it's 25.5 times 10 to the 20 sigma. The way that this table works, oftentimes it's scaling up that number so that we don't have to use the small numbers here. So for Cl2, the cross section at 330 is actually 25.5 times 10 to the minus 20 square centimeter per molecule. Let me write that again. So cross sections are typically very small numbers. Okay. So then we would take that 25.5 times 10 to the minus 20. We would then take the right. So that would be for cross section. We would then calculate the flux. Okay. And then we would calculate, and this is a good assumption here. Assume 1. Okay. So let's say we wanted to also do this for bromine, right? If I'm now scanning across, hopefully what we can gather is we wouldn't necessarily pick the same wavelength, right? We'd have to pick the lambda max for bromine. So scanning across for bromine, we can see that that's occurring right around 420 nanometers for bromine, right? So we would have a different lambda max there. So I did the calculation for bromine. So let's write that down. Let me see. Sorry, change the color. So lambda max for bromine, or excuse me, the cross section, 64.8 times 10 to the minus 20 square centimeter per molecule. So if we were to now calculate energy of light at 420 nanometers, so I did that calculation already. So let's see, where did that go? That works out to be 4.73 times 10 to the minus 19, and technically that would be joules per single photon. So now to calculate the flux of that situation, and let's assume we've got 1 watt over 1 square centimeter. So that would have units of 1 joule per second. That's the same as 1 watt. All over that 4.73 times 10 to the minus 19 joules per photon. And then if we have that very simple assumption that it's 1 square centimeter area, then we can see the joule and the joule cancel, and we'll be left with 1 over seconds, 1 over photons, 1 over square centimeter per second. So that gives us the right unit, and we get something like 2.11 times 10 to the 18. That's going to end up with units of photon over seconds per square centimeter, right? So that was square centimeter over photon right there. Okay, and then per second. So now let's see. Did I do the formula correctly? Power divided by energy times area. Okay, yes, that was right. All right. So now if we continue on with that calculation to get Kp, we'll assume that the quantum yield was 1 molecule per photon times the cross section. So that was, let's see, it was 64.8 times 10 to the 20, there, to the minus 20. 64.8 times 10 to the minus 20 square centimeter per molecule. And then times the flux that we just calculated, 2.11 times 10 to the minus 18 photons per second per square centimeter. What we can see here is the molecule and the molecule unit cancel, the photon and the photon unit cancel, the square centimeter and the square centimeter unit cancel, and we're left with 1 over seconds. And so if we were to carry out that calculation, you can see here that the, that's to the minus 20 and to the positive 18. You finish off that calculation, but what I wanted to show you here is that the Kp values are typically, around 1 to 10 or so, right? So 18, yeah, so 13.6, right? So I said between like 1 and 100, so that was pretty good. So 13.6 1 over seconds. So in other words, if you pick the right lamp source and you pick the right wavelength, photolysis rate constants can be driven in quite a customizable way, right? So we could have picked more power, right? And that would have made the rate constant go faster. However, if we would have kept that same power over a larger area, right, that would have diminished our flux, which would have decreased our photolysis rate constant. Of course, all of this, in the laboratory, right, we can customize. If we were thinking about how to calculate photolysis rate constants for things going on planet Earth, like photochemistry happening in the atmosphere, we can't customize that, right? We have to calculate it based on however much light is available from the sun, which turns into quite a hideous and complicated calculation. Okay, folks, that's it for this module. Apologies there for the wonky calculations. I'll see you in the next and final module for the semester, which will be module 10. All right.